Now, time to get into the meat and the bones. I have no idea how long I've been going, but hopefully not too long that you are still listening. So there's been a lot happening. Obviously, a lot of you people know that I am very into space and kind of what the heck is going on out there, right? And there was a little something that happened a couple days ago, and it was in our Milky Way galaxy. At the center of our galaxy is a giant supermassive black hole that has been able to be observed based on the stars that have orbited around it. And this was something that I was taught very early in college once I started getting into my minor of astronomy. Um, they would talk about and they would show us this image of, well, it was more of like a GIF or GIF, however you pronounce it, but a short video of the stars that were orbiting around the center of the Milky Way. And they were orbiting super fast and they were kind of moving very at extremely high speeds. Like we're talking a certain percentage of the speed of light. So we're talking super fast around this certain point that's in the middle of our Milky Way galaxy. And so over years, like 10, might have been 10 years, could be off about that, but over a certain number of years, they observed a certain spot around the center and they kind of pitched along all these photos of this stuff. I'm not sure what light they were observing in, but I don't. It definitely wasn't optical because it's the center of our galaxy. So you got to think about how much crap you got to look through to see down there. So that's kind of where they thought that there would be a supermassive black hole because it just they weren't able to see anything, and based on the size of what it would have to be really small and really dense. And most cases, that's a supermassive black hole, which is very common at the centers of galaxies. Like the other one, 2019, the M87 galaxy, which I'm not too sure where that is. I can't, probably should have looked that up. But where that is in a different galaxy. But that is, we were able to get a photograph of that black hole, and that was released in 2019, and that was using the Event Horizon Telescope, which is basically telescopes. I believe they're radio. I believe uh, all across the Earth. Not sure how many there are, but there are. Let me actually look that up right now. I don't want to be wrong about that, but I do believe that there's 6. Let me see. How many telescopes? 8 observatories. Okay, so I was off. Okay, but back to what I was saying. So they're placed all across the Earth, and what they do is they combine together to kind of make a telescope that's the size of our Earth to kind of look at these things because these things are very far away. Um, and it's very hard to be able to go see them. And so, yeah, they use this to observe this black hole at the center of our galaxy, and they were able to get a picture of it. And first off, I wanted to talk about to kind of introduce this is what Stephen Hawking had to say about black holes. So in his book, A Brief History of Time: From the Big Bang to Black Holes, it's a updated edition. I don't know what's updated about it, but I haven't actually read through the entire book yet. I'm not very good at finishing books. I know recently I talked about reading Animal Farm, but I really haven't read all that many books front to back page. I do want to start getting into that though, but sometimes I'd rather just scroll through TikTok or Instagram or play video games. Unfortunate, I must say. But going back to Stephen Hawking, in chapter 6 of his book, A Brief History of Time. Here we go. He does start off his passage talking about, quote, by the wave-particle duality of quantum mechanics, light can be regarded as both a wave and a particle. Under the theory that light is made up of waves, it was not clear how it would respond to gravity. But if light is composed of particle, one might expect them to be affected by gravity in the same way that cannonballs, rockets, and planets are. So that's how he starts in the first paragraph, kind of laying the groundwork of light is and kind of what it means to be like, because he's talking about a black hole and he's going to go on further to talk about what it actually is and the more fundamental mechanics of what a black hole is. So he's talking about light, because black hole is something that the mass is so large that not even light can escape it. And this kind of lays the groundwork that if light was a wave, then I think he's saying, under the theory that light is made up of waves, it was not clear how it would respond to gravity. So it's not clear if it's a wave, but if it's a particle, we know that particles have mass and therefore are affected by gravity. And so he's kind of bringing up that idea first to kind of talk about the theory of there being no light. And so that's kind of how he introduces black holes. Then he talks about the history. And then he kind of talks about the certain people who did a lot of the measurements of what the density, mass, size, all of the different parameters that it would require for something to become a black hole. That could be a star, that could be a planet, but there's a certain limit in which a thing of a certain mass can shrink down to the size of, in terms of radius, diameter, to become a black hole. And they've been studying this a lot. I know with like the Large Hadron Collider, they've been studying this a lot too. So a lot of cool stuff. And then there's this really cool passage in which he talks about, which is the reason why I thought of this book. It's a fairly long passage, but it's kind of detailing what if you were watching a black hole happen, kind of what that process is. And this is something that I learned in my class. But this example by Stephen Hawking is a really good example, because I've watched a lot of YouTube videos of what it would be like to take a spaceship and drive right up next to a black hole. I mean, we saw that in Interstellar. One of my favorite movies, just because I like science and space, black holes, all that kind of stuff. But that example is a really cool example. And so there's this passage, page 97 of A Brief History of Time by the great and wonderful Stephen Hawking. I'm going to read this. It talks about the collapse of a star into a black hole. So let's start right here. In order to understand what you would see if you were watching a star collapse to form a black hole, one has to remember that in the theory of relativity, there is no absolute time. Each observer has his own measure of time. The time for someone on a star will be different from that for someone at a distance because of the gravitational field of the star. Suppose an intrepid astronaut on the surface of the collapsing star, collapsing inward with it, sent a signal every second, according to his watch, to his spaceship orbiting about the star. At some time on his watch, say 11, the star would shrink below the critical radius at which the gravitational field becomes so strong nothing can escape, including light. And his signals would no longer reach the spaceship. As 11 approached, his companions watching from the spaceship would find the intervals between successive signals from the astronaut getting longer and longer. But this effect would be very small before 10:59:59. They would have to wait only very slightly, more than a second between the astronaut's 10:59:58 signal and the one that he said when his watch read 10:59:59. But they would have to wait forever for the 11 signal. And this is talking about time. Talking about like if he's doing this on a watch. Further, it goes on to talk about light waves emitted from the surface of the star between 10:59:59 and 11 by the astronaut's watch would be spread out over an infinite period of time, as seen from the spaceship. The time interval between the arrival of successive waves at the spaceship would get longer and longer. So the light from the star would appear redder and fainter and fainter. Eventually, the star would be so dim that it could no longer be seen from the spaceship. All that would be left would be a black hole in space. The star would, however, continue to exert the same gravitational force on the spaceship, which would continue to orbit the black hole. Then he kind of gives a disclaimer and kind of goes on. This scenario is not entirely realistic, however, because of the following problem. Gravity gets weaker the further you are from the star, so the gravitational force of our intrepid astronaut's feet would always be greater than the force on his head. This difference in the forces would stretch our astronaut out like spaghetti, or tear him apart before the star had contracted to the critical radius at which the event horizon formed. However, we believe that there are much larger objects in the universe, like the central regions of galaxies, Sagittarius A star, or M87, like I'm going to talk about today, that can also undergo gravitational collapse to produce black holes. An astronaut on one of these would not be torn apart before the black hole formed. He would not, in fact, feel anything special, as he reached the critical radius and could pass the point of no return without noticing it. However, within just a few hours, as the region continued to collapse, the difference in gravitational forces on his head and his feet would become so strong that again, it would tear him apart. Interesting stuff, I must say. I really do recommend that you get this book because I like this kind of stuff is like so cool. So cool. It was just really impactful on me when I was in college. We read this book about black holes in by Kip Thorne, I believe. Not sure about I don't know why I can't remember the name of that book, but I think it was talking about black holes. And it's just such a fascinating thing. I really like this stuff. I'm a huge buff of it because these things actually exist. And it's like, it's something that is so foreign to my day-to-day life. And it takes a lot of things macro for me. It makes me think a lot about, well, what are we? Where are we? I'm in Pittsburgh, Pennsylvania right now, in the United States of America, but I'm on planet Earth. And I'm in a very specific solar system, in a very specific galaxy, in a very specific location in the universe. And I think that's so cool. That's awesome. And it makes me feel very special, very lucky to be alive at this moment in time when we're able to look out and actually take still images or a combination of images and put them together and take a picture of these black holes. Because I mean, I always believed that these things existed, but to get video proof of it is something else. It's really cool to see, literally. But it's always been a super cool thing to me. And for in the last couple paragraphs of this chapter, there was something really cool that I was seeing as I was looking through this book again before the podcast. On page 110, it says, and it is talking about other black holes. For example, observations with the Hubble telescope of the galaxy known as M87 reveal that it contains a disk of gas 130 light years across, rotating about a central object 2,000 million times the mass of the sun. So 2,000 times 1 million. That's how much more times the mass of the sun that this object is. This can only be a black hole. And then goes on further to say, very high energy particles would be generated near the black hole by the falling in matter. The magnetic field would be so strong that it could focus these particles into jets ejected outward. And that's one of the major things about M87, and the reason why we were able to discover these things. I believe they're called quasars, and that might be a separate thing, but they shoot at these gamma rays. I believe they are gamma rays, and they shoot out all over, and we're able to here detect them on Earth because they will be pointed at us. And I believe that's one of the ways that they found M87. I could be completely entirely wrong, but just super cool stuff. And what I wrote there was photo 41019 right next to the M87. So I thought that was pretty funny, because I remember when I wrote that down, I was sitting in my kitchen at home. I was home from college. It could have been spring break. It would have been the fourth month, January, February, March, April. So it was April. I think I was still in school, in class at that time. I believe. But I was able to see that, and that was something that was mind blowing to me, because I was starting to get really into space, and I was reading this book at the time, obviously. And when that announcement came out, I remember I was at my kitchen table. I had my laptop out, same laptop I'm recording this podcast on, had that, and I was looking at this picture, and I was like, let me go get my book, because I remember reading that passage, and I plopped that in there, and that was kind of when that was one of those first ones where I was like super into a new discovery, where I was really on top of like the space news. Before that, most of the stuff was just me going through classes, but this was like one of the times where outside of the class I was starting to get into like these space topics per se. And so then I started looking into the James Webb Space Telescope after that as well. So that's how I got really into that, was from outside of class. And one of my projects in my senior class was to talk about that specific telescope, and that was really cool to do. But yeah, and so now I'm gonna kind of shift over and talk about Sagittarius A star. Behold, this is the first photo of the Milky Way's monster black hole, Sagittarius A star. So this article is by Keith Cooper, published 9 days ago on space.com. The image was taken in the light of sub-millimeter radio waves. So I was correct. They were taking this image with radio telescopes. So they had those observatories all over the Earth, and then they were able to kind of get a better picture of it. So I think right off the bat, we have to say it is not a visible light spectrum. If you were there, this is not what you would be seeing. This is not in the visible light spectrum. This is not red, green, blue, whatever light. And so I'm going to actually pull this up right here, because now is actually a good time to talk about this. I'll probably bring this up later. But I'm going to go over here. Okay. All right, now I'm sharing my screen for those who are just listening. It is the light spectrum. It's a graph of the light spectrum. And as you see, the shorter that you get, so 10 minus 12 meters in terms of length of the wavelength, all the way over to 10 to the third meter, so a kilometer length of the radio wave. And right in the middle, 400 to about 700 nanometers, that's the visible light spectrum. And on the shorter side of that, so the shorter wavelength, is ultraviolet. That's the stuff that will get people like me very bad sunburns. And then on the right is infrared, and that's kind of longer. So the reason why they were doing that, and let me stop sharing, is because as you can see, radio is right around 1 millimeter. That's how long the wavelength of it is. So, or 1 meter, sorry. 1 meter is about where radio is. And so you have to remember they were looking at this through radio light. So let me stop the share right there. So what they were doing was looking through radio, because once you get so far into the middle of a galaxy, especially a galaxy of our own, which we are inside of, there's a lot of gas and a lot of crap in the middle of it that you have to be able to look through. So if you use something that's not of a correct wavelength, there's going to be stuff that's going to block it. But in order to look through it, you're going to have to look at a longer wavelength. Like you can look at the sun in different wavelengths. There's different filters and different wavelengths that some cameras have as well, where you can see longer wavelengths. And so that's how they were able to take a picture of the supermassive black hole. And so kind of with that being said, the article later goes on to talk about how they were able to find it. They actually were looking at the M87 galaxy, that black hole, and also the Sagittarius A star black hole as well at the same time. But because they are in different parts of the universe, different sizes, and they have different properties about them as well, they came out at a different time. Like, for example, the Sagittarius A star is much closer, yet much smaller, and also around the center of it. Let me actually pull up the picture of it. I'll go to this article and screen share it. For the people that are just listening, it is the literal picture of Sagittarius A star. Just write in, once again, it's space.com. It's an article about it. And you can look up it, Sagittarius A star black hole picture. Look that up online as well to kind of see. You see these 3 dots around it. And you can see, yeah, that's the radio waves that are coming from this specific spot in the Milky Way. So that's the black hole right there. All right, let me stop the share. So yeah, that's pretty much what they were looking for, and so they got that one out. But the thing about that one is it would change based off of it was based off the multitude of movement around the event horizon, that black part in the middle. That's the accretion disk. So that is matter that is around the black hole that is orbiting it, but is doing so at such a speed that it brings off those kind of radio waves. So that's kind of what that is. And so we have some people. I kind of want to see. Here we go. Later talks about Sagittarius A stars being starved. Quote, we only see a trickle of material making it all the way to the black hole, Harvard astrophysicist Michael Johnson said during the NSF press conference. Quote, in human terms, it would be like eating just one grain of rice every million years. End quote. Why the accretion of gas into Sagittarius A stars is so slow has been a puzzle for many years. A lot of mysteries with it. People are getting a 2020 Nobel Peace Prize for finding the mass. It is 4.3 million times the mass of our sun. So that's a little crazy. It's a little heavy, if you must say. A little yikes. Okay, and then it kind of talks about the physical computers. This is kind of cool. Yeah, they talk about the reason why there's those three dots is because it was like a combination picture of multiple images stacked on top of each other to kind of get an average of what the thing would look like, what the black hole actually looks like in totality. So it's not a single image. It's a collection of images that is being kind of all gathered together to create one image. That's kind of what the image is. And so you'll see those kind of three dots that are surrounding it is places where there was the most amount of radioactivity. And that's why that picture will be like that. But in talking about the physicality of it here on Earth, it says in the article to try and explain what they are seeing. The EHT team, which is made up of more than 300 researchers across 80 institutions, performed more than 5 million supercomputer simulations to try and find one that was a match for what they observed. We were left with only a handful of simulations that share the features that we observed, but none of them explain all the features. Very, very interesting. And then there's a lot more on this as well, talking about the measurements of it. I'm going to go to a different article. I should probably share these so people aren't just looking at me and kind of see what I'm looking at. It's a good thing about Zoom, man. Recording these on Zoom, it's not the best camera quality, but where am I at over here? Not the best camera quality, but which is a good thing. Once again, apologize to those listening. I'm gonna take a bite out of the watermelon. Maybe 2 bites. Very good. So this is an article on The Print. Quote, the title is "The Story Behind Capturing First Photo of Sagittarius A, Milky Way's Supermassive Black Hole. While it may seem a little scary, it's reassuringly far. It happens to be the same size and the size a donut would have on the moon. So if you put a donut on the moon and tried to look at it, that's about how big this black hole would look on our sky. There was a person who I saw do a video on this. If you're looking at your view of the night sky, or to take like a look on I forget how you describe it. So I guess the basic concept is 180 degrees, and then you break that into 60, I believe. So from 180 to 60. Each degree is 60 arc minutes, I believe. And then within those 60 arc minutes, each arc minute is 60 arc seconds. And then under 60 arc seconds, there's another one. And then you divide that number by like 1,000, and then you're able to get it. It's something like that. It's something crazy. I don't think they talk about it in this article. I don't think they really talk about it. Okay, so they kind of talk about it. The team observed Sagittarius A star multiple nights for many hours in a row, similar to using long exposure time on a camera. Okay, kind of talks about this. Yeah, so it kind of just talks about the M87 in all of its glory and the difference between these two. Like that one was in 2019. This is 2022. And I mean, that was my first thought. Once I found out that the Event Horizon Telescope, which once again is a collection of telescopes, once I found out that they were searching for both M87 and Sagittarius A star, I was like, well, isn't the Sagittarius A star one like a lot closer? But the M87 galaxy obviously is much further away. Center to our Milky Way galaxy from Earth is about 27,000 light years. And it's a, let me look that up right now, actually. Okay, let me stop share because I cannot type into here. All right. How far away is M87? Galaxy M87, 53.49 million light years. That's how far away M87 is from us. So it's good to know. Very good to know. All right, and then I kind of want to look at this too. That's not what I wanted. Let's do a quick screen share. Let's go desktop 2. Boom, let's pull it up. All right, so what we're looking at right here is a comparison of the sizes of the two black holes, M87 and Sagittarius A. The two black holes. All right, kind of gives a brief little description, size comparison on the two black holes imaged by the Event Horizon Telescope. M87 at the galaxy Messier 87 and Sagittarius A star, the center of the Milky Way. Shows the scale of the two in comparison and other elements of the solar system, such as orbits of Pluto and Mercury. Also displayed is the sun's diameter and current location of the Voyager 1 space probe, the furthest spacecraft from Earth. M87, which lies 55 million light years away, is one of the largest black holes known, while Sagittarius A star, 27,000 light years away, has a mass roughly 4 million times the sun's mass. M87 is more than 1,000 times more massive. So it's big. Because of their relative distances from Earth, both black holes appear the same size in the sky. I believe Sagittarius A star is bigger, but it's not by much. Not by much. So kind of the image that we're looking at right here. Okay, good. I'm screen sharing right now. You're kind of able to see in this picture, you can see M87 on the left and Sagittarius A star on the right. And they actually show Sagittarius A is able to fit inside of the M87 galaxy. And so kind of what's shown here is Sagittarius A is about the size, the relative scale of it is Mercury's orbit around the sun. You kind of see in the middle of it the sun's diameter, which is a little tiny dot. And then you go and put Sagittarius A on the inside of the M87, and you can see it's very small and kind of right outside of the middle of the black hole, you can see Pluto's orbit. And now Pluto's orbit takes many years to complete a full trip around the sun. So you can imagine how big that circle would be. And that's kind of like the sun's diameter in the Sagittarius A. That's kind of what it looks like. Then on the very outskirts, heading into the high intensity radio waves, the kind of ring that goes around, right in the beginning of that is where Voyager 1 is. And now Voyager 1 is the furthest probe from Earth. So just looking at these kind of shows you the insane size of M87, and then combine that with the distance away. It's crazy, man. It is crazy. That kind of size is something that I can't even think of or fathom. Like even the size of something that is pretty much the size of Mercury's orbit in total circumference and size is something insane. The biggest thing that I can kind of imagine, I guess, is the sun, but even that is still insane to think of because there would be about 300 of our planets that fit inside of our sun. And it's just crazy once you get up to that large of a scale. And then also you can go opposite way and come back down. It's just crazy, crazy stuff. But to kind of continue on with this, I wanted to show this video of a size comparison. Now, for those watching the video, you can see Sagittarius A star is 27,000 light years away, and the M87 galaxy is 55 million light years away, and appears only slightly different in size. And this kind of, as the video starts out, it kind of looks like the M87 is a little bit bigger. It's kind of hard to see. But anyways, it's a video of the two by the European Southern Observatory of the two black holes. And I'm going to play the video now, and you're going to see them both at the same distance away from each other and kind of see the difference in actual size. So the M87 is now about 30 million light years away, almost twice as big. So we're going to stop the video right now at about 20 million light years away. It's about double the size of Sagittarius A. So we're cut in half pretty much the distance, and it's over twice as big already. And then I'm going to stop with 10 million light years away. That's kind of what it looks like. Once again, people who are just listening, this is size comparison of the two EHT black holes. Video is done by European Southern Observatory on YouTube, posted May 12th, 2022 for you to watch. But for those watching the video, it gets even crazier. So we're 10 million light years away, and it seems as though inside of the ring and the black hole itself, it looks like you could fit Sagittarius A star. And we're 10 million light years away. Sagittarius A star, still 27,000 light years away. And then we go to, just look at this image. Once again, people, I'm 17 seconds into the video. If you go 17 seconds, you're about, was that 3 million? Yeah, 3 million light years away. And it's already taking up half of the display of the screen on my video. So this thing is just a monster, humongous. And then we're going to go to, I'm going to try and go 27,000 light years away right there. It does not even make sense at this point what image we're looking at. This is right at 18 seconds in the video, and you couldn't even tell the difference. You can't even tell that M87 is even anything. It's really weird. Really funny, I should say. Really funny to see that. And so I'm going to stop the share right there. Just the pure size difference is something that is insane to see. And I mean, without seeing it, you really can't tell, like, okay, so it's 1,000 times bigger. Okay. It's how far away? Okay. It's hard to visualize that 55 million light years compared to 27,000 light years. You're like, okay, that's a lot. But once you're able to visualize it, once again, people, size comparison of the two EHT black holes on the European Southern Observatory YouTube page is where you can watch that video. Fantastic. Fantastic. It's so cool to look at. But now I kind of want to shift gears for another second and kind of talk about another thing that I touched on earlier, which is the James Webb Space Telescope. So let me pull it up right here. The James Webb Space Telescope can now track moving targets in our solar system. Now can study planets, their satellites, and more in our neighborhood. This was posted May 20th, 2022 by Brad Bergen. Not sure how to see the difference. It's going through the James Webb Space Telescope. For those who do not know, it is the largest telescope that we have put into place, or into space, I should say. It's kind of the thing that's an upgrade of Hubble Space Telescope, which has made a lot of discoveries in our universe and really helped move science along as a whole. And so then, I mean, you're having this guy come in, this James Webb Space Telescope. For those watching, uh, this is it on the left in a composite image of several NASA images on the right. But over on the left is what the space telescope will actually look like. Now it is in a uh, far away. It's like a million miles or something away from Earth in its own orbit at the Lagrange point too. I've talked about it in an earlier video. Um, but yeah, so it's pretty far away from the Earth and it's facing away from the sun. It's got these huge heat shields on it to help block um, a lot of the sun's energy. Um, so here we go. We got quote. Who is this quote from? I think it's just from NASA. Okay, the next step is to carry on the testing to track other objects moving at different speeds to confirm Webb's effectiveness in studying the wide variety of objects zipping about in our own solar system. Quote, I'm really excited about Webb's upcoming first year of operation, said Webb's interdisciplinary scientist for solar observations, Heidi Hanmel, in the blog post. Okay. I lead a team of equally excited astronomers eager to begin downloading data. So they go on to talk about kind of, yeah, it can look far away in that radio light that we've talked about. But still some things in our own solar system that we can look at that definitely are not as far away. So, and then here is MIRI fields juxtaposed to Uranus, including its rings. A picture of this. This is a simulated spectra of Uranus, a wealth of atmospheric chemistry. So this is looking at the atmosphere and its contents according to the wavelength of certain chemical compounds such as oxygen, water, nitrogen oxide, but a bunch of different certain materials that they are able to see through this graph that you can see. This is something that I had to do in college that I really don't know too much about. As I assume many of you know, I'm not the smartest person when it comes to this. I just have a huge interest. Frankly, I just really like this stuff. I think it's cool to see, but I'm not perfect on this. And then as we go down, looking more and more at certain things. Once again, this is interestingengineering.com where you can find this article. And so here's a picture of Webb could also help us uncover subsurface oceans on Europa. And it's a graph of observable flux in terms of wavelength of kind of what's going on with Europa. A lot of people believe that there's water underneath the surface of Europa, and it could be harvesting life out there. It could be life in that water that has been able to adapt and live there over a period of years. And so this is kind of looking at I believe once again, this is just a simulation of what it could possibly do. So I don't think this is actual data, but it's looking at the difference of chemical compounds that's on it. Yeah, could it help us uncover the mysteries of Europa's oceans? Surely with other fascinating planetary bodies like Europa, which emits plumes thought to stem from vast subsurface oceans and many more, the James Webb Space Telescope will become a crucial link in solving some of the most profound questions in astronomy, planetary science, and astrophysics, not only at the farthest reaches of the ancient universe, but here in our solar system as well. Very, very cool kind of stuff. Mr. Brad Bergen. Interestingengineering.com is where you can find that article. And now moving on. One of the first things that came from the James Webb Space Telescope is this image of a grouping of stars. And it is one of the earliest images from it, but it's also one of the coolest. So space.com published, as I'm recording this now, May 21st, 10 days ago, by Elizabeth Howell. NASA's James Webb Space Telescope is almost ready for science. Here's what's next. The first science work for the $10 billion project should start in the early summer. All right, and so you can see this image in the beginning of the article, and it's a comparison of views of the same part of the sky as seen by NASA's retired Spitzer Space Telescope and the newly launched James Webb Space Telescope. And the difference between the two is insane. It's like you're looking at something through one through 1080p and the other through 240p. It is insane the difference in just how they two look. And I mean, yeah, they talk about it being $10 billion. Could last as long as 20 years. I think I've talked about it. They plan to do 10 years with it. It's going to perform regularly. There are 17 scientific instrument modes that will come online in the next 2 months. A new tracker on NASA's main website allows the public to track the progress. Let's actually go to that right now. Let's check the progress. Here we go. We got a nice little thing. Currently, right now, this is live. This is 1:12 p.m., May 21st that I'm looking at this. There's a lot of stuff. So it's in its full out at orbit motion right now. Currently, as we're looking at the hot side and the cold side, because it's facing away from the sun right now. So the hot side is currently now it's out in the middle. It's out there, man. 89 degrees Fahrenheit, 305 Kelvin, and 55 Fahrenheit and 286 Kelvin, both on the side that is facing the sun. Then on the cold side, so that is where the telescope will be, because you have to think you're looking in radio waves. You don't want anything to heat up. You want it to be as neutral of an image as possible. Negative 384 degrees Fahrenheit and negative 393 degrees Fahrenheit, 37 Kelvin on that cold side, which is where the instruments are. And then on the specific instruments, the specific mirrors, negative 449 degrees, 6 Kelvin, negative 390, and so on and so forth. So it's very, very cool to kind of see where it is right now. And that's another one where just looking at that, studying that outside of my class, it's something I got really interested with. And it's currently right now, it's currently pretty much almost done, I think. I really have no idea how to read this, in all honesty. To track testing of all 17 modes. Is 17 modes done? 17 modes. Instrument modes. Here we go. Okay. All right, so I guess these are all done. Okay. Roger that. All right, not sure what we're looking at. Sorry about that. So yeah, it's pretty much up and running almost. It's kind of cool. Oh, here we go. Here we go. Kind of giving a description of what I talked about earlier. So here in this space.com article, additionally, Webb's operational capabilities will be tested, most especially its ability to track objects within our own solar system, which move much faster in the telescope's view than distant objects, as well as the observatory's ability to hold precise alignment as it changes targets. Additionally, wavelength calibration will be performed to make sure Webb is correctly recording the luminosity and spectra, and kind of definition is a fingerprint of light that allows scientists to identify what elements are present of its targets. So recording the luminosity and spectra of its targets. And once again, spectra is kind of that graph for those who are looking at watching on the past article that I was talking about. You can kind of see the graph and the difference in wavelength versus the spectra, and kind of see what elements were present on planets, and that's kind of what they're doing, man. And so yeah, once again, here's the electromagnetic spectrum. So as you can see, more energy, shorter wavelength, less energy, longer wavelength. We use the radio waves, or the radio frequency, to kind of see deep into the middle of our solar system, into other galaxies as well, to get through all of that gas, all that super thick, gas clouds of hydrogen, helium, all that kind of stuff, which will form into stars, collapse in on itself, form into stars. Kind of what happened here. According to theory, obviously we have not been around long enough to see this happen in action, to my knowledge. I'm not a scientist, like I think I have to say every 5 seconds. Not a scientist, not an expert on this stuff, but just interested. So kind of looking at moving onwards and upwards. Here's it gets ready to probe the universe's chemistry. Kind of talked about that in my last one. This is also space.com. This is by Elizabeth Howell, published March 4th, 2022. The James Webb Space Telescope instrument gets ready to probe the universe's chemistry. The near-infrared spectrograph passed initial checkouts amid the observatory's mirror alignment activities. Kind of talking about what it's going to be doing in our own little place. And it's talking about she talks about the difference in alignment of the mirrors and stuff like that. But I was looking. And there she is, contributing writer. Very cool. Very cool. So yeah, that's kind of where I'm gonna stop with the space talk, man. So I guess big picture thing is, I love this space stuff, man. And it's really cool that we're able to find hard evidence that things like black holes that Stephen Hawking has talked about, that we're able to get physical still images of them. And be able to look at them and understand them. It's one of the things I'm super excited about. There's a lot of stuff going on in politics, a lot of stuff going on with the economy here in America. And I just frankly hope that we're able to do more stuff like this in the future. And I hope people really understand just how important it is to be um, thinking in the macro a lot. That's one of the things that I do a lot, is thinking about things outside of yourselves. I'm not talking about spirituality, religion, or anything like that. I'm talking about kind of looking at not that we're living on Earth, but that we're living in the universe. And to realize that there are, in fact, these things out there kind of puts a lot of things, at least for myself, in perspective, in terms of, I think often about the fact that there has not been signs of, maybe not even signs, but direct evidence of life out there in the universe. Not yet. And I think currently you gotta love what you got right now, because I don't know if we're gonna detect life With the James Webb Space Telescope, maybe we'll be able to detect life on a moon of Jupiter, like Europa or Saturn or any other places in our solar system, much less our own galaxy, much less the rest of the universe, where we'll find life or signs of life at least. I really don't know. And to see things like these giant black holes out there and prove that these are indeed real kind of puts a lot of things in perspective for me, because then you talk about the sheer size of how big some of these things are. It puts a lot of things in perspective, like, hey man, like there are things much bigger than you. There's bigger things to worry about in this world. And that's been really helpful to kind of keep things in perspective, keep the problems however big they are. So we all have problems, but I think one way to kind of get through a lot of stresses and a lot of anxiety, things in your life where you're like, oh crap, is to think about the bigger picture. That's something that's helped me a lot. And that's something that I've really adopted into looking at, not only within myself, but in my general daily life. Is like, listen, man, there's freaking black holes out there that are swallowing up billions and billions and billions and billions of pounds, tons, whatever it is of stuff. And these things are out there and they are in the central to these galaxies that are out there as well. And frankly, really cool to see stuff like this is finally being uncovered, because I think it gives me hope that, or further is more evidence. I wouldn't say evidence, but it makes me be like, wow. Every time I hear like a new update about one of these black holes at the center of these gigantic galaxies, such as our own, that we're on a little small planet able to see, makes me kind of be like, wow, man, we're who knows what the heck's going on out there? Who knows? These things actually exist and they're actually in the central parts of galaxies. Crazy, crazy to think about. And frankly, I love talking about this stuff, man.